Hello. In this movie, we're gonna continue our discussion of monetary care. So we are studying. So we are trying to solve this problem. So this is our objective function, and we have a constraint. This is our constraint, and we want to choose x and d. So we want to solve this problem, and last time what we did is we found how to draw this constraint in our graph. So it turns out if we draw this graph, so we have x here, d here. So we draw this constraint in this picture, then we have a graph something like this. So there is a kink at this point here. So we have here we have h, here we suppose u is here. So this is our constraint, and now we want to draw something like indifference curve here. So let's look at our objective function right here. So remember, when we study consumer's problem, so consumer's utility maximization problem. So remember, we want to maximize consumer's utility subject to budget constraint. So when we want to draw indifference curve using this utility function, what do they do? So in this case, when we want to draw indifference curve, so remember, slope of indifference curve is MRS. So we know this from undergrad microeconomics class. Slope of indifference curve is MRS, and we can find the slope of indifference curve using this formula, mu1 over mu2. Here, mu1, this is marginal utility from first consumption good, and mu2 is marginal utility from the second consumption good. So if we suppose first consumption good is apple and second is banana, mu1 is marginal utility from apple and mu2 is marginal utility from banana. And here mu1, we find mu1 as partial derivative of utility function with respect to first variable q1. And we can also find mu2 using similar formula. So partial utility of utility function with respect to q2. So we're gonna use this formula here. So what we want to do here is we want to draw something like indifference curve using this objective function. So imagine that this function is something like a utility function. Then let's think about MRS. So we're gonna use this formula over here. So we get minus. In numerator, we have mu1. So mu1 is a partial derivative of utility function with respect to q1. So we're gonna use this idea here. So we are going to think about partial derivative of this objective function with respect to our first variable x. So if you take partial derivative of our objective function with respect to x, we get 1 plus b prime x d. So think about taking, take this function and think about taking derivative with respect to x, then you get this numerator. And in the denominator, we're gonna take derivative with respect to d, then we get px. This formula over here represents slope of something like indifference curve. And if you look at this formula, so let's look at this formula. Suppose x is very small. So x is very small. So if x is very small, what is the sign of this formula? Is it plus or minus? Remember from extant probability function, we know that it has this kind of shape. If x is small, let's say x is very small, so x is here. X is very small. We can see that slope is very steep. So slope is very steep. Slope is negative and it's very steep. It means p prime x is a really big negative number. So it's gonna be really big negative number over here. So from our formula, so here, this number p prime x is gonna be really big negative number when x is small. Then numerator itself is gonna be a big negative number. And look at the denominator. Denominator is a probability. So denominator is a probability. So this is a positive number. So if the numerator becomes negative and denominator is positive, because of minus sign here in front of this formula, this entire expression is gonna be plus, so positive. So if x is a small number, this formula is gonna be plus. So it means if we draw something like indifference curve, when x is small, slope of this indifference curve is gonna be plus. What if x is a large number? Again, in this picture, suppose x is a big number, then we can see that here, if you look at this slope, it's getting very flat. So it means slope is getting close to 0. So slope is getting close to 0 as x is increasing. Then what do we know? Again, from our formula over here, p prime x, so let me use blue color. So p prime x, this number is getting close to 0, so it's gonna disappear. Then numerator, we have number 1, so numerator is positive. And look at the denominator, it is a probability, so it's a positive number. So because of this minus sign in front of this formula, this entire expression is gonna be negative. So if we draw something like indifference curve using our objective function, it's gonna have a negative slope when x is a big number. Then what we know, so here remember we want to draw something like indifference curve. So when we think about utility maximization problem, we draw indifference curve using the objective function. It is something like this. So look at this indifference curve here. Slope is always minus. So slope is always minus. So if you look at this indifference curve, it is downward sloping. So slope is negative, so downward sloping curve everywhere. This is because, remember, slope is MRS, and this is a formula for the slope. And because marginal utility is always positive, because of this minus sign, MRS is always minus. So this means if we draw indifference curve in our consumer's utility maximization problem, indifference curve is downward sloping curve with minus slope. But in this case, it's different. Slope is plus when x is small, but slope is minus when x is large. Then how do we draw something like indifference curve using this information? So when x is small, it is plus, so it means it's something like this. When x is large, it is minus, so it's gonna be something like this. So this means if we want to complete this kind of graph, it's gonna be something like this. So this is the graph we want to draw here. So when we draw something like indifference curve, then it's gonna look something like this. So let's give the name for this curve. Remember, in consumer's utility maximization problem, the name of this curve is indifference curve. So why this name of indifference curve? Is because if you fix one curve, let's say, so you draw one indifference curve, then imagine any point on this same curve, let's say point A and B. So if you compare A and B, we can say that consumer's utility is the same. So consumer is indifferent between A and B. So consumer is indifferent between A and B. So we give name indifference curve for this curve. Now, we want to give a proper name for our curve over here. So let's go back to our objective function. So if you look at this objective function, so look at this objective function. So look here, we have x. So x is a level of effort, or it's gonna translate to care cost. So x is cost. So x, this first part can be considered as accident care cost, and this is accident probability. So something goes wrong, then we multiply d. So what is d? So look at the constraint. If injurer is not judgment proof, injurer is gonna pay h. Injurer is judgment proof, then he's gonna pay just whatever he has, and that's it. So we can imagine that D represents injurer's liability cost. So if you look at this objective function, we can interpret this objective function as cost for injurer. So we can interpret this objective function as cost for injurer. Then let's go back to our curve over here. Then imagine these 2 points CD. So remember, this curve has exactly the same meaning as the indifference curve. So the difference is just interpretation. So what's happening at point C and D? At point C and point D, this cost must be the same. So we interpret this objective function as injurer's cost. So this curve right here is connecting all the points in this picture that represent the same amount of cost. So at point C and point D, injurer's cost is the same. So not just C and D, imagine any point on this curve. The cost for injurer in our objective function is exactly the same. So interpretation of this curve is exactly the same as indifference curve, just the names and terminology is different. In our utility maximization problem, we had the indifference curve. So if you choose an indifference curve, then we find these 2 points with the same amount of utility, just like that. In our picture over here, you find one curve, then all the points on this curve represent the same amount of cost for injurer. So cost is same on this curve. So we can give this name ISO cost curve. So we call this curve as ISO cost curve. So ISO cost curve means this curve represents same cost. So if you look at this point, let me use another picture. If you look at this curve, it has a positive slope up to a certain point, and at this point it has a max, and then afterwards this curve has a negative slope. So this is the shape of our ISO cost curve. So our ISO cost curve has inverted U shape. Now we want to think about this max point over here. So look at this point. So look at this red point over here. So look at this red point. You choose one ISO cost curve, then at this red point it attains the maximum. So in other words, what's happening? Slope is exactly equal to 0 at this point. And from our previous formula, slope of our ISO cost curve is given by this formula. So this is the formula for the slope. And at this red point, the slope is equal to 0. So this expression must be equal to 0 at this red point. At this red point, slope is equal to 0. Then look at the denominator. It is a probability, so it's not equal to 0. So if this expression is equal to 0, it means numerator must be equal to 0. So in other words, so numerator must be equal to 0. So this means we have this equation, and this equation looks very familiar to us. So we fix one isocost curve, then we can find the maximum point here. And what's happening is at this maximum point, we should have this equation. So at this maximum point, we should have this point. Okay. Then so let's think about drawing many isocost curve over here. So our question here is, if I draw two isocost curve, so here is the maximum. Do we have graph something like this? Or do we have graph something like this? So in the first picture, the maximum point is moving to the right. So maximum point is moving to the right as we go down the isocost curve. And on the right side, maximum point is moving to the left as we go down the isocost curve. So which is the case? So let's see. So think about two isocost curve. So we're gonna imagine two isocost curve. Let's say first one is I1, second one is I2. So we're gonna think about two isocost curve. And first isocost curve has a peak at, let's say, x1 tilde comma d1. And second one is x2 tilde comma d2. So using our previous graph, so we suppose isocost number 1 and isocost number 2, and if you look at isocost number 1, it has a max at x1 tilde and d1. And if you look at isocost number 2, it has max at x2 tilde and d2. Okay. Okay, then remember one thing. D1 and D2 cannot be the same. So D1, D2 cannot be the same. Why? Suppose they are the same, then what's gonna happen? Suppose they are the same, so I draw two cost curve and D1 and D2 are the same. Then what's gonna happen? D1, D2 same. And let's say x1 tilde is here, x2 tilde is here. Then first isocost curve has a peak at this point, so it's gonna be something like this. Then second isocost curve has a peak over here, so it's gonna be something like this. Then if you look at this graph, it's wrong. Why? Because look at let's say blue point A and blue point B, and look at blue point C. Cost must be the same between A and B, right? This is I1, this is I2. Cost must be the same between A and B because A and B are on I2. And B and C must be the same because B and C are on the same isocost curve I1. So A and B are the same because they are on the same isocost curve I2, and B and C must be the same because they are on the same isocost curve I1. Then it must mean cost must be the same at A and C. But this cannot be true because remember, we go back to our original objective function. So remember, our objective function is this. So objective function is this. If you look at point A and C, x is the same. So x is the same. So x is the same. But if you look at point A and C, so look at C first. So let's say this is x3. If you look at point C, it is represented by x3, comma, let's say this is certain number of D, let's say D3. And if you look at point A, it is represented by x3, comma, D4. So as you can see, D4 is bigger than D3. So at point C, cost is x3 plus p x3 times d3. At point A, cost is equal to x3 plus p x3 times d4. But as we can see, d4 is bigger than d3, so cost cannot be the same. Cost must be different between A and C. In particular, at point A, we should have higher cost for injurer. So therefore, this cannot be true. In other words, D1 and D2 cannot be the same in the beginning. So we have this problem over here because we supposed D1 and D2 are the same in the beginning. So this cannot be true. So when we choose two isocost curve, the maximum point cannot be the same. So in particular, the value of D cannot be the same for the maximum. So this is why in the previous note, I said either we have this kind of indifference curve, isocost curve, or we have this kind of isocost curve. So isocost curve cannot intersect each other, and the reasoning is exactly same as in indifference curve. So let's suppose D1 is bigger. So let's suppose D1 is bigger. So if we suppose D1 is bigger, then so I1, indifference I1 has a max at this point, and I2 has a max at this point. And we suppose D1 is bigger, then remember what's happening at the maximum point. At the maximum point, we know that slope is exactly equal to 0. So remember we had this formula. So for the second isocost curve, we also have this formula at the maximum. And if you compare these two equations, left-hand side is the same, so right-hand side must be the same as well. Right-hand side must be the same as well. So right-hand side must be the same as well. And we assume D1 is bigger than D2. So D1 is bigger than D2. Therefore, if we want to make both sides the same, this part must be bigger than this part. So because D1 is bigger than D2, this blue part must be bigger than this blue term on the left-hand side. So we should have this inequality. And what does it mean?